We're going to look at conversions for temperature. Okay, we know how scientists like to measure temperature, which is
Kelvin.
Kelvin, okay, or Celsius. Most of the time Kelvin. 273. Okay, so to go from Fahrenheit to Celsius, this is a formula that's used a little bit less often, so you might have to have this one down. But this is going from Fahrenheit to Celsius. Again, not super common, because the U.S. is the only one that uses Fahrenheit, okay, or one of the only. To go vice versa, you're going to use the inverse of that fraction. Okay, it's the opposite. Again, not very common. Hopefully you all know how to go from Celsius to Kelvin, okay, or Kelvin to Celsius. It has to do with the addition or subtraction of 273.
How was the conference?
It's good. 98.6. So now let's convert 98.6 to Celsius, see what our average body temperature is in Celsius. Yeah, Jose, do you just know that?
Yeah.
Like we know 98.6. What is it?
I think 36.
36? Around 36. What did you guys get when you calculated it?
37.
37. Okay. Yeah, pretty good. All right, nice. So, Jose, I should have had you go the other way from Celsius to Fahrenheit. All right, very good. Okay. All right. We've talked, or you should understand, hopefully, the concept of thermal equilibrium, but we're going to review it just a little bit. So, when we have two objects placed in contact with each other, over a period of time, they'll form something that we call thermal equilibrium, okay? Which means that the energy transfer between those two objects eventually balances itself out, right? To reach an equilibrium, that means we've reached a balance, okay? So when the energy transfer has stopped, when the energy transfer has ceased, we reach what we call thermal equilibrium, in which both of these objects would now have equal temperatures, okay?
Ice and water.
Yeah, that's a really common, easy example to see, right? When we put ice in water, there's a transfer of energy between that water and that ice. Eventually, it's going to reach the same temperature, which is just water, right? It happens really easy and really visibly to all liquids, right? At room temperature or to the temperature of the fridge or whatever that it's in there. A good example. Right? Anything else that we can think of? That's all we got?
What would you say?
Yeah, I can see that. Eventually it's going to even out, but yeah. Yeah. All right, yeah, good. Okay.
You're wrong.
We're going to continue with the zeroth law of thermodynamics. Have we talked about this before? Have you heard of the zeroth law of thermodynamics? Right. It came after the first three, but then they decided it needs to go first, so they made it the zero. Yeah. All right. So this is kind of wordy example, but easy to visualize if you think about it. Okay. So if two systems are in thermal equilibrium with a third, then they have to all be in thermal equilibrium with each other. Okay. So if A is equal to B and B is equal to C, what does that mean about A and C? They have to be equal to each other. Okay. Yeah.
I thought it was kind of like self-explanatory.
Well, I thought you would think so too, but yeah. You gotta write it down. That's why it's a law. Okay. Yeah, I'm not sure why they felt the need to really verbalize this principle. Okay, but I did. Again, this has to be after a point in which both of those systems have reached the thermal equilibrium, right? We could have a really cold thing of water and a really hot thing of water, but unless they've reached the thermal equilibrium, it's not going to count for the 0th law, right? They have to have reached the thermal equilibrium together, and then we see a full circle, kind of. Okay, so that's the 0th law. Now, the expansion of materials, okay, something called thermal expansion. When do we see things expand in terms of temperature?
Isn't it when you put pop in a freezer and it'll explode?
Yeah, a little different, but okay. In most common circumstances, when do we see things expand?
I'm gonna go
Hotter they get.
The hotter they get or the colder they get? Okay, think about your fingers.
Cold.
When do your rings get tight?
When it's
Oh,
cold.
when your circulation is like.
No, when it's hot.
Yeah.
When it's hot and you have clammy fingers, your fingers start to expand. Okay? You never noticed that before? Okay, I know you don't. Guys don't usually wear rings.
When it's cold.
No, I don't think so.
No, I'm thinking the same thing. Like when we put like something in the freezer and it just gets too big, it like explodes in the freezer.
Okay.
Oh yeah.
Yeah, that's different. That water is a very specific property that expands when it's cold. That's different than almost any other substance.
Hey, does it pop do that too?
Yeah, but pop has water in it.
No.
Yeah. No. Yeah, okay, I can see.
Is arthritis, like, if you have arthritis, like, isn't that really warm?
All right. So, for the very vast majority of materials, most will expand when they are heated and shrink when they are cooled. Okay? Next time you are working with your hands, or it's hot outside or whatever, look at your fingers and see if you notice that they're swelled. Or better yet, when it's really cold, you'll see your fingers kind of like shrink down. They get really kind of thin looking. Okay, I'm not saying you're going to lose 10 pounds, when it's cold, but you'll see your fingers, or you'll start to feel your fingers kind of just be a little colder, okay, or thinner. Okay, but the amount of expansion or contraction really does depend on the materials. Okay, and we have some constants that help us deal with that. But we're going to look at the change in length of a material as proportional to the change in temperature. So we'll deal with delta L and delta T. Here is our equation for the thermal expansion. We get new letters again. Okay, delta L equals alpha times L sub 0. What's L sub 0 mean? Initial, good. Right, so initial length times change in temperature. Okay, and alpha is what we call the coefficient of linear expansion. The coefficient of linear expansion. And those values are on page 388. So why don't you go ahead and look at that table, and we'll talk about those values.
Oh, this does not sound fun.
So what do we do if you have like an alloy?
Ooh.
A mixture between those two, you mean?
Ooh.
We do need to change it to Kelvin, that's right. Oh, wait, no, you don't. No, you don't. No, you don't. Because look at our coefficients of expansion. Their unit is a reciprocal of Celsius. So, sorry, you can keep it in Celsius. Okay, so we're going to solve this basically both ways. We're going to solve what's the change in length when it's heated, and we're going to find what's the change in length when it's cooled, and then we'll be able to combine those two answers. Okay, so we know L initial is 200. We know our initial temperature is 20. Okay, and what is our coefficient of steel?
12 times 10 to the negative 6.
Yeah, 12 times 10 to the negative 6. And that says iron or steel. Yeah, realistically. Okay, so we would say
Are we going to heat or?
change in L. You can go either way first, but I'll go probably heat first. 12 times 10 to the negative 6 times 200 times change in temperature. So change in temperature would be final minus initial, so I'll go 40 minus 20.
Yes.
So then when we want to find how much it has contracted, we would say final minus initial. Okay, so that means the amount or the length of that steel bed could be anywhere from 199.88 meters to 200.048 meters. Okay, we see there's not, it doesn't look like a lot of difference here, but when you scale that down and look at it in terms of centimeters, right, that's 4 whole centimeters that thing is going to expand or contract. Again, it doesn't seem like a whole lot to us, but on the other side, when it cools, it's going to shrink up to 12 centimeters. Okay, so I know it doesn't look like those numbers vary a lot, but when we put it down into a little bit more manageable numbers, it's easier for us to see. Okay.
Damage to a bridge.
Yeah, it could. Yeah. I think engineers most likely take that into account when they're building it, but yeah, it could cause damage if we see extreme temperatures one way or the other. Yeah, it doesn't get negative 30 all that often. Okay. Just like think about this.
Can we leave it in centimeters? No? What? Diameter of the rod and the inside diameter of the rod.
Actually, I don't really care if you leave it in centimeters. I don't really care. Either way.
What?
Yeah, that's what I thought.
Oh, okay, this makes sense now.
What's the component? Is it still the same one?
So you try to get the ring
The
bigger.
coefficient.
The coefficient, yeah. It's an iron ring. Yeah, so do we envision what's happening here? We have a cylinder that this ring needs to fit over. Okay, it gives us the inside diameter of that ring, and it tells us it needs to be 0.008 centimeters larger than the rod, which we have the diameter of as well. Okay, so we need to do what to that ring to get it to fit onto the cylinder? We got to heat it, right? We got to figure out what it needs to be heated. So to what temperature does the ring need to be heated to be fit? Sorry, I missed a word there. Okay. All right, so let's start looking at what we got. Okay, the ring itself is 6.420. The cylinder is 6.445. What does the diameter of the ring need to be?
6.453.
6.453, and we got that by taking the diameter of the cylinder plus 0.008, right? Does that make sense? We need the ring to have a diameter of 6.453 centimeters.
Should your answer be really small?
My answer's pretty big. I'm not sure I got it right.
0.008 is not the delta L because we don't want the ring to go just from here 0.008 larger. We need it to be larger than the rod itself. So the ring is going to have to expand this minus this, which is really 0.033 centimeters.
Oh.
Right? Does that make sense?
No.
Delta L, okay.
Not at all. Not at all.
Still not? Okay. Let's say it one more time. Okay, so delta L is going to take what we need on the ring minus the original diameter of the ring, which is 0.033. Okay, and that's going to equal the coefficient, which is 12 times 10 to the negative 6, because it says it's an iron ring. Original length of the ring. Yep, 6.420, not length, it's really diameter, but essentially we're looking at length here. And then we need delta T. Okay, we're solving for final temperature.
So X minus 20.
Yep, and our original temperature was 20.
Oh, you gotta add 20. So X 20. It's X minus 20. 3 plus 20. Yeah.
We're going to take 0.033 divided by the coefficient and divided by 6.420. Then we add over that 20.
Oh, okay.
Okay.
I don't know what I did.
Hey.
Okay, and your equation for volumetric expansion is very, very similar.
Oh, what is that?
That Greek letter is called a, anybody know? Beta. You can keep it in liters. Oh, it's 1,000. To go. Oh, sorry, I don't know. I thought you said liters to milliliters.
Liters to gallons?
Okay. So we're solving for delta V here. Our coefficient of gasoline is 950 times 10 to the negative 6th. Our original volume is 70, and our temperature goes from 20 to 40.
What was your coefficient? 950.
It's for gas.
Gasoline. Did we get about 1.33 liters? Yeah? Okay. Looked at just the expansion of the gasoline. Now we need to look at the tank itself. Would those be the same values?
Besides the code.
Yeah, everything except the coefficient would be the same, right? The coefficient would change.
0.049. Because that's what
You did that the first time.
That's what you know the first time.
0.049. Because I did that the first time.
Okay, so knowing what we know, sorry, go ahead and solve for the tank.
What? You'll have the
Well, they should be easy then. Okay, you don't have to write down everything on this. You've seen Boyle's law before, Charles' law, and combine. Okay, just write down the actual equation. Probably you might even have it memorized. Okay, but we see an inverse relationship between pressure and volume. So that means if one goes up, the other goes down. Okay, one goes up, the other goes down. If you don't know this conversion between liters and cubic meters, you might want to put that down, right? 1 cubic meter is equal to 1,000 liters. we like to have our volume measured in liters, and we like to have our pressure measured in atmospheres. We like to get on that habit because in the ideal gas law, that's what we want to use. Okay, liters and atmospheres. Okay, P1V1 equals P2V2. Okay, Charles' law. Does anyone remember what Charles' law is?
You saying
It doesn't have pressure, or is it over?
Doesn't have pressure. Volume over pressure. V1 over T1 equals V2 over T2.
Charlie Brown is always on.
Mm-hmm.
I remember that. That's funny.
Okay, so we have constant pressure in Charles' law, which means we keep volume and temperature. Volume has to be in liters. Temperature has to be in Kelvin. Okay. For the other units, it's not as essential for these equations, okay, because it's a multiplication and division relationship between liters and milliliters or whatever, cubic meters and liters. It's a multiplication relationship. Temperature is just addition, so it throws off our ratio if we don't add that 273 to our Celsius temperature every time. Okay, if it was multiplying by something to get to Celsius and Kelvin, they would end up canceling each other out. Since it's an addition conversion, we have to have that converted to Kelvin every time. Okay, these two are directly related, which means if one goes up, the other goes up. One goes down, the other goes down. Okay, direct relationship. Okay, Guy-Lussac's law drops which of the components? Yeah, Guy-Lussac's law just does pressure and temperature as a direct relationship, which means their equation probably looks like P over T. Good. P1 over T1 equals P2 over T2. Okay, a direct relationship. One goes up, the other goes up.
What goes up? Gotta come
What's it called? The combined gas law. So cleverly named, the combined gas law. Okay, P1, V1 over T1. If you know just this one, you can find all the other gas laws from this one, right? So if you're going to memorize one, make it this one.
Oh no, I don't have. I don't think I can. Is this so awesome?
You have a party? Graduation party?
Yeah.
Just got some bullets? Party? What?
Okay, the ideal gas law next.
Mrs. Coach again.
Okay.
I'll never forget that. I remember just thinking, what? Like, LOL.
All right, here is our constant for our. Sounded a little pirate-ish. Okay. No, same one. A little pirate-esque. Okay, the reason that I like to use this R is the units that go with it. We like to be liters, atmospheres, moles, and Kelvin. Okay, so we like to have all of those units. That's why this R works. 0.0821. What does the N stand for?
moles.
Moles, number of moles. N stands for number of moles. P is pressure, V is volume, R is our constant, and T is temperature. Will you ever have to solve for R?
No.
No, because we know it. It's a constant. It works in any equation with any ideal gas. Okay, what do we know about STP? Standard temperature and pressure. Anyone know the...
1 ATM,
Yeah.
273 degrees.
Very nice, very nice. 1 ATM and 0 degrees Celsius, or realistically 273 Kelvin. We want to keep that in Kelvin. Because if we plug in a condition of STP at 0 degrees Celsius, that would kill all of our multiplication and division problems, right? Because we can't multiply or divide by 0, right? So we want to make sure that we're at 273. We're not in Celsius there. Okay. So if we say it's at STP, we know 1 atmosphere and 273 Kelvin. Okay, those are conditions that you will need to have memorized.
Jeez. Oh, notes.
This is all review.
What is that volume?
This is just something that you might know off the top of your head, but we're going to prove it anyway. Okay, what's the volume of 1 mole of any gas at STP? Okay, so ideal gas law, remember, is not a before and an after type situation, right? Ideal gas law is when we get only one set of conditions. Okay, so pressure is 1 atmosphere. We're solving for volume. N is 1 mole. R is 0.0821. Temperature is 273. Does that number ring a bell?
Yes.
22.4 liters. What's that called? What's that principle that we just solved for? What's that called?
Oh, it's the thing.
Molar mass.
Avogadro's principle.
It really is.
Avogadro's principle. That's what that's called. So Avogadro told us that 1 mole of any substance at STP is going to have a volume of 22.4 liters. Any substance moving ideally, performing ideally, or acting ideally has a volume of 22.4 liters. Okay.
I don't know.
All right. Don't pay attention to the answer down there.
I didn't even notice it was down there until you.
All right. A helium balloon has a radius of 18 centimeters at 20 degrees Celsius, has a pressure of 1.05. How many grams of helium is in the balloon?
I don't know.
Well, we're going to find out. Okay, first of all, let's think about this. If we wanted to find grams, what do we need to solve for first to get there? Moles. Has to be moles. And what gas law equation can we use to solve for moles? Has to be the ideal gas law. Okay, so actually we're solving for moles. Okay, we know that temperature is equal to 20 plus 273, so 293. Pressure is already in atmospheres, which is good. We know our R value, 0.0821. We don't know our volume, but luckily we were given the equation for volume of a sphere. How many of you knew that already? Nice. I did not.
Shout out to
I would not have. Okay? So we need to find the volume of that sphere.
Do you gotta change that to centimeters?
Since we know the conversion between meters cubed and liters, we could do that. Or since we know that 1 milliliter is equal to a centimeter cubed, we could keep it in centimeters. It doesn't matter. Okay, so that's another conversion you might want to put on your equation sheet, that 1 centimeter cubed is equal to 1 milliliter. That's another conversion for volume. Okay, so I'd probably go ahead and convert to meters since we want to be in liters anyway. Okay.
So 1 centimeter cubed equals 1 milliliter.
1 centimeter cubed equals 1 milliliter, and then I think 1 meter cubed equals 1,000 liters. Right.
0.02.
Well, just chill. Let everybody else.
Chill.
Okay. Volume is 4/3 times pi times r cubed, so 0.18 cubed. All right, I'm going to go ahead and put it in meters.
It's like 2 days.
Okay, that's in meters cubed, so can we use that directly? No, we got to convert it to liters. So if we know that a cubic meter is equal to 1,000 liters, we would take that, multiply by 1,000. Okay. Do we see how we went from cubic meters to liters? We multiplied by 1,000. So 24.4 liters. Now we can solve in the ideal gas law.
But
Oh gosh.
To convert from moles to grams, what do we do?
I don't know.
We do something with the molar mass. We multiply by the molar mass of helium.
Not one.
I'm trying to like split.
No, that's
Like 4.1.
Just 4.
I think it's 4.
Hey, see that?
About 4 grams.
Okay.
How do you not see
Where?
it?
Alright, rewrite my lines.
It's up at the top right corner.
Under HE.
Oh, okay.
4.26.
Alright.
Okay, which means our grams of helium, 4.26 grams. There you have it.
55. Sure.
Okay, as one goes up, what happens to the other one?
As one goes up, they both gotta go up.
Okay, yeah.
What is it? Scott.
Direct relationship. Okay.
It's a song.
Okay.
Gee, I thought you just made
Alright, relax.
Tell me what your final pressure was equal to.
2.18. 2.18.
2.18.
If one goes up, they both have to go up.
One goes up, the other goes up. Okay, so cross multiply and divide here. We should have gotten a pressure of 2.18. What's our units?
ATM.
Atmospheres.